afternoon, students. This is again Pragnesh Polara from Home Engineering College, Junagadh. In this session, we are going to discuss the topic of eigenvalues and eigenvectors for the given matrices. Here, in the last sessions, we have already learned about the matrices and the basic things of matrix. Okay, so now here we are going to discuss how to find the eigenvalue and eigenvector for the given matrix, and what do you mean by the eigenvalues and eigenvector. And we first of all we quickly discuss some basics of eigenvalues and eigenvectors. Then we will discuss some example which are most important for the exam point of view. Okay, so if we look at the PPT here, today we are going to discuss about eigenvalues and eigenvectors. So this is the definition of eigenvalues and eigenvector. So if we have given a square matrix A, then a non-zero vector x is called an eigenvector of matrix A if we can find a real number lambda such that Ax is equal to lambda x. Okay, so note that first of all here A is a square matrix, that means we can find the eigenvalues and eigenvector for the matrix only which is square matrix, right? Second thing, the eigenvector which is vector is non-zero vector, so eigenvector never be zero, and the eigenvalue is a real number which may be equal to 0 and which both satisfies the equation Ax is equal to lambda x. So the vector x which is satisfies the equation Ax is equal to lambda x for any value of lambda, then that is known as lambda is known as eigenvalue of matrix A corresponding to the eigenvector x. Okay, so here lambda is the eigenvalue and the corresponding eigenvector is x. So this is the definition of eigenvalue and eigenvector for the given matrix. Okay, so let us look at in the next. Here note that the zero vector cannot be the eigenvector, as I told you that eigenvector never be zero, so zero vector cannot be the eigenvector even though a0 is equal to lambda into 0, but then too zero vector never be the eigenvector, but lambda is equal to 0 may be the eigenvalue because lambda is equal to 0 is positive, but by the definition eigenvector never be 0. So here 0 never be the eigenvector, but lambda is equal to 0, that may be the eigenvalue of the given matrix. If we look at one simple example, here the question is, so that x is equal to 2 1, that is the vector, is an eigenvector for A is equal to 2 minus 4 3 minus 6. So here if we find the Ax, because if we need to prove that 2 1 is the eigenvector, then we need to prove that Ax is equal to lambda x for some lambda belongs to R. So here Ax is equal to 2 minus 4 3 minus 6 multiplied by 2 1. So by matrix multiplication we will get that is equal to 0 0, right? So 2 into 2 minus 4 into 1, that is equal to 0, and 3 into 2 minus 6 into 1, that is equal to 0. So Ax is equal to 0 0, and if we take lambda is equal to 0, then lambda into x, that is equal to 0 into 2 1, that is also equal to 0 0. So here if we take lambda is equal to 0, then Ax is equal to lambda x. So for the lambda is equal to 0, 2 1 is the eigenvector for the given matrix A is equal to 2 minus 4 3 minus 6. So note that here 2 1 is x, that is x is an eigenvector of A, and the lambda is equal to 0 is an eigen value for this eigen vector, right? So this is a simple example of finding eigenvalue for the given eigenvector, right? So if we look at something more about the eigenvalues, then if we let x be the eigenvector of the matrix A, then there must exist an eigenvalue lambda such that Ax is equal to lambda x, or equivalently we can say that Ax minus lambda x is equal to 0. That means if x be the eigenvector of the matrix, then there exists an eigenvalue lambda that such that Ax is equal to lambda x, and Ax is equal to lambda x, or equivalently we can say that Ax minus lambda x is equal to 0, or equivalently we can say that A minus lambda I into x is equal to 0. So if we define the new matrix that is equal to A minus lambda I, if we say that A minus lambda is equal to B, then Bx is equal to 0, right? Because A minus lambda I into x is equal to 0. If we say A minus lambda is equal to B, then B into x is equal to 0. So if B has an inverse, B is a matrix, and if the inverse matrix of B exists, then x is equal to B inverse into 0, right? That is equal to 0. So x is equal to 0, which is the 0 vector. But as we all know that eigenvector never be 0, so that means B inverse cannot be possible. That means B is non-inversible, so that we cannot find the inverse of the matrix B. So if we remind our basic knowledge, when we cannot find the inverse of any matrix, so answer is we cannot find the inverse of the singular matrix, right? Because if the matrix is singular, then the determinant of that matrix is equal to 0, and if the determinant of the matrix is 0, then the inverse is not possible. So here B inverse is not possible. That means the determinant of B must be equal to 0 if x is the eigenvector of the given matrix, right? So if we follow this argument, then we can say that it follows that x will be an eigenvector of A if and only if B does not have an inverse, as I told you, or equivalently we can say that determinant of B is equal to 0, because if determinant of B is equal to 0, only then inverse is not possible. Determinant of B is equal to 0, that means B is equal to A minus lambda I. So here determinant of A minus lambda I is equal to 0, which is called the characteristic equation of A, and we can use this characteristic equation to find the eigenvalues for the given matrix A. Okay, if we solve this equation, determinant of A minus lambda is equal to 0, then we can find the solution, or we can find the roots of this equation, which are known as the eigenvalues of the matrix A. So note that determinant of A minus lambda is equal to 0, and by solving that equation we can find the values that is known as eigenvalues. Okay, so let us look at one example of finding eigenvalue for the given matrix. The question is, find the eigenvalues of the matrix A is equal to 2, minus 12, 1, minus 5, right? So as we all discussed that the characteristic equation is A minus lambda I, determinant of A minus lambda I is equal to 0. Here right hand side 0, so we can also say that A minus lambda I or lambda I minus A, that both the same thing. So here I have taken lambda I minus A, determinant of lambda I minus A, that is equal to lambda minus 2, 12, and minus 1, lambda plus phi. This is lambda I minus a. If we take a minus lambda I is equal to 0, then also we will get the same answer, right? So by solving this determinant, we will get lambda square plus 3 lambda plus 2, that is equal to lambda plus 1 lambda plus 2. As we have discussed that for the eigenvalues, the characteristic equation is determinant of lambda I minus a, that is equal to 0. So if we take lambda plus 1 into lambda plus 2 is equal to 0, then we will get lambda is equal to minus 1 and lambda is equal to minus 2. And as we discussed, this value or the solution of this characteristic equation is known as eigenvalues. So here the eigenvalues for the given matrix A is minus 1 and minus 2. So here minus 1 and minus 2 are the eigenvalues for the given matrix A is equal to 2, minus 12, 1, minus 5. So in this way we can find the eigenvalues for the given matrix. Let us look at one more example of the eigenvalues and eigenvector. And before we solve that example, we need to look at two definitions which really connected with the eigenvalues. Okay, so the order m for the lambda of an eigenvalue lambda as a root of the characteristic polynomial is called the algebraic multiplicity of lambda. That means order of m lambda, the order m lambda of an eigenvalue lambda. That means if we have the eigenvalue lambda is equal to 1, but that is appears 2 times, that is lambda is equal to 1 is the repeated solution for the characteristic equation. So here we can say that lambda is equal to 1 is the eigenvalue of algebraic multiplicity 2, right? That is the order of lambda is equal to 1. So order of lambda, that is known as the algebraic multiplicity of lambda, right? And the same way, the number small m lambda of linearly independent eigenvectors corresponding to the lambda is called the geometric multiplicity of lambda. That means if we find one eigenvector for the given eigenvalue, then that geometric multiplicity for that lambda, that is equal to 1. If we find the 2 eigenvectors for the eigenvalue, for example lambda is equal to a, then for the lambda is equal to a, the geometric multiplicity is equal to 2. That means the algebraic multiplicity, that is the order of lambda, and geometric multiplicity, that means the corresponding eigenvectors. The number of corresponding eigenvectors is known as geometric multiplicity for the given eigenvalue, right? So these two definitions we need to clear, and so that let us look at one more example so that we can discuss about the algebraic multiplicity. Let us look at the PPT here. That means let's clarify our idea of algebraic multiplicity. If the root of the characteristic equation, that means lambda 1 is equal to lambda 2 is equal to lambda 3 is equal to lambda k, then the eigenvalue is said to be of algebraic multiplicity k, because here lambda 1 is equal to lambda 2 is equal to up to is equal to lambda k. So all the eigenvalues are same. So here k eigenvalues and all are same. So the algebraic multiplicity of lambda, that is k, right? So let us look at this example. Find the eigenvalue of a is equal to 2, 1, 0, 0, 2, 0, 0, 0, 2. And if we find the characteristic equation, then here a minus determinant of a minus lambda I or lambda I minus a, that is lambda minus 2 minus 1 0 0 lambda minus 2 0, 0, 0, lambda minus 2, and that is equal to 0. And this is the upper triangular matrix, right? So if we want to find the determinant of this matrix, we only need to multiply its diagonal elements, right? So the determinant of this, we can easily find, this is the multiplication of the diagonal elements, that is lambda minus 2, lambda minus 2, and lambda minus 2. So that is equal to lambda minus 2 cube, that is equal to 0, which is the characteristic equation for the given matrices. So by solving this one, we will get lambda is equal to 2, but here lambda minus 2 whole cube is equal to 0. That means lambda is equal to 2 is repeated 3 times. So we have lambda is equal to 2 3 times, so that we can say that lambda is equal to 2 is an eigenvalue of algebraic multiplicity 3. Here there is a printing mistake, there is eigen, lambda is equal to is an eigenvector, there is a printing mistake, there is an eigenvector printed. So that is the eigenvalue of algebraic multiplicity 3. Okay, so this is the idea about the algebraic multiplicity. Here this is some result about the eigenvalues and eigenvectors. So note that eigenvalues and eigenvectors are only defined for the square matrices, which I have already told in the starting of this session, that eigenvalues and eigenvectors possible only for the square matrices. Second thing, eigenvectors are not unique. That means if V is an eigenvector, so is KV. Okay, that means eigenvectors are not unique. The third thing, suppose lambda 1, lambda 2 up to lambda n are the eigenvalues of A, then the trace of the matrix, we all know about the trace of the matrix, which is the summation of the diagonal elements, that is known as the trace of the matrices. Then the summation of all eigenvalues lambda 1 plus lambda 2 plus lambda 3 up to lambda n, that is equal to